Hey guys, hello everyone and welcome to the channel. Welcome to a new series of video which we are starting on this channel. The series name is going to be Smart Question Series hashtag SQS, and this is going to be your daily dose of smart problem solving. Now a few days back I asked you guys for suggestion of the name for this particular series, and I got some really good suggestions, some very creative names, and including them, considering them, and adding my own ideas into it, I come up to with this particular name. So this is going to be our new series of video, and we'll be discussing a question on this particular series till the upcoming exam. So the idea of this series is to take a question, discuss about that question, and also to add upon it to understand the concept from where the question was asked and to understand the gist of the concept. Okay, that's the main idea. And I'll try to take more and more challenging question. If you have some suggestions of question, or if you have some question which you guys want me to solve or want me to discuss in this series, you can drop them down in our like on our email, or you can let me know if you have the question ID or something like that. You can let me know in the comment section. I'll try to include that as well. So that's how it is going to do. Okay, so for this particular video, this is going to be the first part of this series, and for this I thought of taking one of the most challenging topic from chemistry, and that is quantum chemistry, which many of you will agree upon it. So I have taken a question which was asked in CSIR June 2024, the very latest exam, and a question which was asked from quantum chemistry, and let's try to understand it. Okay, let's directly come up with the question. And yeah, so this is the question which I'm going to discuss in today's video. This question was asked in CSIR June 2024 exam, and the question says that consider a arbitrary unnormalized wave function psi expanded in the terms of Eigen state of Hamiltonian H, where H, when operates on the wave function psi n, it gives you epsilon n psi n, where n is anything from 0, 1, 2, 3, 4, something like that. And it also says that epsilon naught is the lowest energy, then you have epsilon 1, then epsilon 2, and epsilon naught is the smallest, and so on it goes. Then the wave function is expressed to you as that psi is equals to sigma of an and phi n. Okay, now this particular question looks very difficult because a lot of Dirac notations and lot of like psi, phi, and everything they have included in this question, and that's where a lot of people or a lot of students who are not that good with quantum chemistry, or someone who has just studied quantum chemistry from the surface level, might got confused or might have just left this question. Okay, but I'm going to tell you that this is very simple question. Okay, and I'll tell you how to solve this question. So the next thing it says that the correct option which definitely holds for any set of a n is. Okay, now first thing is to understand from where this question is asked. Okay, or from what concept this question is asked. So I'll tell you that, but let me first of all explain you a few more things. Okay, just so that you will yourself understand that from where it is asked. Okay, so let's start from here, that what is the wave function given to you. The wave function, the definition of the wave function is given to you, that psi is equals to sigma till n, and you start from an and you take it from phi n, something like this. Okay, so this is the definition which is given to you. So sigma or summation means you have to add, right? You know that if let's say if it is written like sigma n, what does that means? It means that and if it says that till n, so that means you have to add starting from like 0, 0 plus 1 plus 2 plus 3 plus 4, and you have to keep adding it till n. Okay, so that's what it means. Sigma means you have to add the terms. So if I use the same like the same definition of sigma and try to write down for the wave function, so my wave function psi should be written as, if I expand it and write it down in this way, this should be written as a naught, because first of all I have to put 0 in the place of n, and that's because n starts from 0 according to the question. If n starts with 1, you have to start with 1. Okay, so it depends upon what is the definition given to you in the question. So a0, and then you have phi 0, and this is the bra vector of it, and then you have the ket vector of it, and then you have then you have to put the other value, which is 1. So you have a1 and then phi 1, then you have a2 and then you have phi 2. I'm not doing anything. I'm just putting the value of n, different values of n, and I'm just using the definition of sigma, okay, summation. That's what I'm doing. So this can be written as like this, right? A3, and you can keep writing it like this, and you have to keep writing it till what? Till the value of an, and then you have phi n. Now you don't have to worry about these things, okay? This is called as ket vector, by the way, okay? This is called ket vector. In case if you are not aware about what this ket vector is, so I have discussed this in detail, and it's very simple. It's very simple. It's just like what you have studied in normal quantum chemistry. It's just the way of notation, okay? It's called Dirac notation, and I have discussed this in my short video. You can watch that video. I'll give you a link of that video, okay? There I have discussed what is Dirac notation, and I have explained you all these things. So this is a ket vector, so nothing to worry about it. It's just like a normal phi. You can consider it as a wave function phi. This is about your wave function psi, okay? The next thing is that you have a Hamiltonian, which is an operator, and it operates on these ket vectors, okay? And it gives you certain values of energy. Certain value of energy is what you are going to get from there, okay? And followed by and that's what it is given. So this is nothing but a eigenvalue equation. You can consider it as eigenvalue equation. So you are operating operator Hamiltonian on the wave function. You are getting eigenvalue of as the energy or the epsilon, and the wave function back. So two things you understood, that this phi or this particular wave function, this is nothing but, this psi is nothing but a linear combination of different atomic orbitals. So this is like a linear combination of atomic orbitals. Why this is linear combination? Because they are being added, okay? So you call it linear combination of atomic orbitals, and these orbitals are like different phi values. These are the different phi values, and then you have a Hamiltonian getting operated on it. And what they are asking in the question, they are asking the relationship with the energies of it. So if you have studied a concept, the concept is called as variational principle. Variational principle, or there is a part of variational principle which is called as linear combination of atomic orbital. Now these things I have already discussed on my channel itself, okay? So I have discussed in a simple video where I have explained variational principle in detail. So I'll give you a link for that again in the I button. You can click on that video and watch that. Variational principle has been explained super easy manner, okay? And that is one of the very high viewed videos, and like you will be able to understand the concept easily if you watch that video. We have variational principle and we have the wave function. Let's try to understand variational principle. What does it says, okay? And we will talk about the linear combination part of variational principle. So the linear combination or the variational principle for linear combination of atomic orbital, okay? So the variational principle for linear combination of atomic orbital, what does it says? It says that if you have a wave function psi, which can be written as, let's call it psi 1. So if you have a wave function psi 1 which can be written as the linear combination of two orbitals, let's say we have c1 phi 1 plus c2 phi 2. So this is a wave function which is written in the form of linear combination of two orbitals, and we have one more orbital, one more wave function, let's say that is phi 2, okay, which can be written as linear combination of three orbitals, okay? So here you have c1 phi 1 plus c2 phi 2 plus c3 phi 3. So that means this wave function can be written as sum of three orbitals, linear combination of three orbitals. And let's say I have one more wave function psi 3, and it can be written as the sum of, let's say, 5 atomic orbitals, okay? So we have c1 phi 1 plus c2 phi 2 plus c3 phi 3 plus c4 phi 4 phi 4 plus c5 phi 5, okay? Now here c1 c2, these are just the coefficients, nothing to worry about it. Phi 1 phi 2 phi 3 phi 4 phi 5, these are all orbitals, okay? They can be wave function, sorry, and they can be written as ket vectors also, nothing to worry about it, okay? Because if you watch my Dirac notation video, you will understand that ket vector and the wave function are not much different. It's just the way how you are representing it. So let's say these are the three wave functions which you have. and they all have their own energies. So if you calculate energy using this wave function, so the variational principle suggests you that how you can find out energy using a trial wave function. Okay, that's the concept of variational principle, where you use a trial wave function and you try to find out energy closest to that actual energy. Okay, so again, to understand this variational principle, just watch that video. I have explained that in super easy manner over there. So if let's say the energy calculated using this wave function is, let's say, E1. Okay, so E1 is the energy calculated using this wave function. According to this wave function, if you calculate energy, let's say the energy comes out E2, and the energy from this wave function comes out E3. Okay, so your like if you want to write down the order of these energies, so according to the linear combination of atomic orbitals, variational principle for linear combination of atomic orbital, it says that the energy which will come up with the highest number of linear combination will be lowest. So the more number of orbitals you will add in the trial wave function or in the wave function to make the or to calculate the energy value will be lowest in that case. And then comes the next one, which is going to be E2, because this one is made up of 5 orbitals, right? This is made up of linear combination of 5 orbitals. That's why the energy corresponding to it will be lowest. This is made by the linear combination of 3 orbitals, so the energy will be little higher over here, and this is made just by the linear combination of 2 orbitals, so energy will be highest. Okay, so this is the order of energy for these three. And if ground state energy or exact energy, okay, is given by E naught. Okay, let's say E naught represents the ground state energy or the exact energy, then the order will be in this way. Okay, the order or the relationship between them will be this, that E naught will be the smallest one, and then your E3, then your E2, and then comes E1. Now remember that the exact energy or the ground state energy is always lowest, and to understand it, or if you want to just get a physical understanding of it, so any system is considered to be stable if the energy is lowest over there. Okay, so the energy of any system in the exact manner or in the way where you are not using any other wave function, in the most stable form, that's called ground state energy, right? So ground state is the most stable state of energy, so that should be lowest in value, right? So that's why epsilon naught or E naught should have the lowest value of energy, followed by the order of the energies, and the order of energy will be decided by how many elements or how many orbitals are linearly combined to make the wave function. So the more number of orbitals combined to make a wave function, the lowest or the nearest it will be to the exact energy. Remember, it will never be equal to the exact energy, because that is these are all approximate methods. If you will study quantum mechanics, you will see that these comes under the approximate methods to find out energy. So it will be very close to the exact energy, but little higher than that. Okay, that's why we have this less greater than or equal to sign. So this is the relationship which we have among all these energy values. Okay, so the whole idea of explaining you this thing was to make you understand that this question is also a linear combination of atomic orbital, and the relationship is being asked between the energies. Okay, now you will say that how this value of energy, we are going to get this value of energy or something like that. Okay, so how are we going to get that? So for that you have to now operate the operator, or you have to find out the energy of corresponding to a particular operator. Okay, so let's try to do that, and let me explain you how you will get to the exact value of energy. Now let's do the fun part. Okay, so the next concept or the next thing which we will apply here is the expectation value. Okay, now you will ask, why expectation value? Because see, whenever you try to find out expectation value of any operator, you get the Eigen value corresponding to that. So because all the relationship here asked in the question is with respect to the energies, okay, and you are given with certain things related to that, so that's why you have to apply expectation value of the Hamiltonian. Okay, and the expectation value of the Hamiltonian is going to give you the energy of that state. So in general, we represent it as, let me just write down, so the expectation value of Hamiltonian of Hamiltonian is given as, let's say H is the operator, we write it down like this, and this is equal to psi star H psi d tau. But this is when the wave function psi is normalized, but in the question if you see, the wave function is unnormalized. Whenever the wave function is unnormalized, you should also divide this with psi star psi d tau. Okay, this is the general form of writing it, or you will say this is the Schrödinger's notation. But in the Dirac notation, if you write down the same thing, okay, so same thing, if you try to write down in Dirac notation. Now, why Dirac notation is important? Because the quotient itself is in Dirac notation. So if you write down the same thing in Dirac notation, this thing is going to be written as phi H phi and divided by. So you will see that this is changed like this. Now, if you will match, or if you just want to see, this is nothing but this psi star is written as a bra vector, whereas psi is written as a ket vector. Okay, so this becomes this, and this becomes this, and because H is in between, so it got sandwiched over there. And in the denominator, this comes like this, and this comes like this, and this like the bar basically comes like that gets sandwiched, and you don't write down integration and all in the case of Dirac notation. So I have just given you a basic idea of Dirac notation. Okay, so why all these things? Because that's what we are going to use. Okay, so now if you just want to answer this question, I'll tell you at the end, okay, the shortcut trick also, but let's go with the concept, because that's what we are here to understand. We are not here to just simply solve the question or just to get the answer. That we will also do, but we also want to understand the concept. Okay, so hold with me. So because in the question itself says that if you operate this Hamiltonian on the phi wave function, you will get the energy corresponding to that and the wave function back. So let's write down this thing which is given to us in the question itself, that if I operate H on phi n, I should get the energy corresponding to that and phi n. And this thing is nothing but the expectation value of the Hamiltonian is actually equal to the energy corresponding to this. Okay, the energy corresponding to this, or here it is mentioned in epsilon, so I should rather write it down in the terms of epsilon. So this is nothing but it gives you epsilon. Now if you want to write down the expectation value of Hamiltonian with respect to phi n, so that can be easily written as like that. You can write down as the Hamiltonian expectation value of the Hamiltonian with respect to phi n. Okay, so this will be written as phi n H phi n. Okay, this is the bra vector, this is the ket vector, and in the denominator you will be having yeah, so you will be having phi n, and yeah, and this should be equal to the energy corresponding to it. So if the normal Hamiltonian operated on psi gives you epsilon energy value, so the Hamiltonian operated on phi n should give you energy En. Okay, so n just denotes the energy state, or the state of the wave function. So here the wave function is of the nth order, so that's why energy should also be of nth order. This is a very important equation. Let's number it something. Okay, now we have to operate this Hamiltonian on the given wave function, which is psi. Okay, and remember this psi is a unnormalized wave function. Okay, that is very important point. And yeah, so let's try to do this, and let's see if we get something out of it. Okay, so yeah, so if I try to find out the energy of corresponding to this psi, for that I have to, or if I just want to find out the I mean I just want to calculate the Hamiltonian for the expectation of the Hamiltonian, expectation value of the Hamiltonian corresponding to psi. So in that case I just have to like write it down in this way. I just have to write down it in this way. Okay, I have to operate the bra vector and then the ket vector, and divided by I have the bra vector and the ket vector. Okay, this is how I will find out the expectation value with respect to the psi. Now, just to make things easy to understand, as I have said that when psi star is this and psi is this, that is just to explain you about that. But since the definition of psi is given to me as it is sigma n a n phi n, so corresponding to that, or just with the definition of it, I'll just write down that since psi is defined to me as sigma or summation n, and I have a n, and I have the ket vector of it. So this is, let's say, phi n, right? This is what is given to me. So this, let's have that this is also ket vector. Okay, so the ket vector of this gives me ket vector. So thus, so this I have taken from my side. Why? Because this is in the terms of ket vector, so I have to also have psi in terms of ket vector. Okay, that's all, just to have them in the same way. So thus, if I reverse this, or if I make it bra vector, this is also going to reverse. Only the wave function get reversed. I mean, the constant does not get reversed. Okay, it should get conjugate of it, but for here it doesn't matter because this is not having any like iota part. So it could be just write it down in this way, that it is n a n, and then I have phi n. Okay, technically if someone is from physics background, he will say that it should have a n star. Okay, that is actually correct, but for here, just to make things simpler, I am not taking that. And because it does not make much difference, because we have a like modulus in the option, so that's why I am not considering that part. Okay, but yeah, that's one of the thing which you should also consider. Okay, let's put it over here. So I should be getting, if I put the values of the bra vector and the ket vector in this wave function, so or in this particular equation, so I should be getting sigma. Okay, I'm just putting the value, okay, for this. So this is going to become sigma a n and the bra vector corresponding to phi. Okay, I'm just taking according to the definition, that's all. Then I have h, so I'll write down h, and then I will write down the value of the ket vector, which is here, from here. So I'll just simply write down the way it is, just the way. Okay, I'm not doing anything any different. An, and then I will be having the bra vector, which is phi n. Okay, or let's make it correct. Okay, let's consider it as star, complex conjugate of it. Okay, that should be actually correct. So let it be like this. Okay, in the denominator we will be having this and this. So again, the value of this bra vector, I'm just going to substitute it from here. So this becomes sigma n, then I have a n star, and then I have phi n, and multiplied by the ket vector, which is sigma summation n, I have a n, and I have phi n. All right, now the thing is that doing summation twice when the things are in multiplication, it doesn't make any sense. So you can take it once, or you can just take it as common. Okay, just do summation once. Both are doing summation from 0 to n, right? So if you can just write it down once, that is not going to make any difference. So I can just take this summation outside. Okay, and I can write it down as psi n, just both of them have been taken out. A n star and a n will come like this. A n star and a n are together, and then the remaining thing is phi n. Then I have h, and then I have the ket vector of phi n, right? And in the denominator, I should be having again the same thing. I will take the summation only once, and then I have a n star a n. Okay, and then I have phi n. So this particular thing, you can see this whole thing is becoming something, right? This is becoming some value, and if you see that value, this is nothing but equal to epsilon n. So in the place of all this thing, I can just write down epsilon n. Okay, and then an star and an star is the complex conjugate that could have negative values, and an is the positive value. So multiplying positive and negative value will give me overall value negative, or and square of it, just like this. If I do -2 multiplied by 2, it should give me -4. If I do -5 multiplied by 5, it should give me -25, right? So basically minus or if I do 5 into 5, that will also give me 25. And if I do 2 into 2, that will also give me 4. So the idea is that if you multiply the same number with itself, you will get the same core value. The sign will only change if the number is positive or negative, right? So complex conjugate can be positive or negative depending upon it. But if I put modulus, modulus will always give me a positive value, right? So if I put the modulus over here, I can write it down as an square. That's the idea. So that's what they have smartly they have done in the options. If you see, they have done in the option like an square and something like that. Okay, so same thing, I am also going to use the same smart technique, and in the place of this I will just simply write down it as summation, okay, or sigma n, and this I can write down as an square and epsilon n. In the place of this I have just written epsilon n from here, okay, and in the denominator I have sigma and I have an square. Now this is giving me, this is the expectation value of Hamiltonian when it is operated on the wave function psi. Okay, this is what we have calculated. This is some value which we have calculated, and this is nothing but this is expectation value of Hamiltonian for a wave function psi. Okay, when you are operating it on the wave function psi. Now you know that this wave function psi was a linear combination of atomic orbitals, lot of atomic orbitals, and you know that according to the variational principle, if you add more atomic orbitals, the energy will be, whatever energy you will get, that will be always greater than the exact energy, okay, greater than or equal to the exact energy. And in this case, this is the energy which you are getting, okay, this is nothing but this is what you have got, or what you have calculated. The expectation value of Hamiltonian is nothing but it gives you the value of energy, right? So here what you have calculated is the energy corresponding to psi. So I'll just write down for your sake so that you understand that this term, which is summation n an square, modulus of an square epsilon n divided by summation n an square, is energy corresponding to psi, okay. And what was psi? Psi is the linear combination of atomic orbitals. So you know that the energy, whatever energy you will get with respect to psi, should be always greater than or equal to the exact energy or the ground state energy, right? This much is what we are using. So here epsilon 3 is what you have calculated. This is the value of epsilon 3, or this is the value of the energy corresponding to this. So that means this energy should be greater than or equal to the exact energy, which is epsilon naught. So what we have got finally is that like sigma n an square epsilon n divided by sigma n an square, this should be greater than or equal to epsilon naught, okay. And this is what you have in your option number A, okay, option number B, and that's how your option B becomes correct option, okay. So you have seen that I have calculated and proved to you that how this comes in. So the idea to understand this concept or to solve this question was, first of all, you should know that this question is from variational principle. Second thing which was used here was expectation value, okay, the concept of expectation value was used to solve this question. And the third thing, of course, is Dirac notation. That was the major gist of it to come up to this particular thing. Now, as I said in the starting that I will also tell you a shortcut trick to solve such questions. See, whenever certain questions or such questions are asked in the form of in the exam and you have to solve certain question, you always have to understand, first of all, you have to find out that what type of question it is. And whenever the question you think or you come up like the question is from the variational principle or linear combination of variational principle, something related to that, your first thing or the first guess should be, because see, shortcut tricks and these things work only on understanding the what is the concept is there and then memorizing something. Okay, so you have to memorize this, that whatever energy you will calculate will always be greater than or equal to the exact energy. Okay, so that means you can simply, with just by knowing that this question is from variational principle and from a linear combination of atomic orbital, your option number A and option number D will be cancelled, because here in these two options the energy which is calculated is less than the exact energy. Okay, epsilon naught is always shown as the exact energy, so it is showing less than exact energy. Here also it is showing less than exact energy, so these two options you can simply cancel out, because whenever you calculate any energy from the variational principle, that will be always greater than or equal to exact energy. So either your option B is correct or option C is correct, either option 2 means option B or C is correct. Now you have to deal with, or because they are very close, you have to just see that whether this psi square will be there or not. So if you have any idea, just a little bit idea of expectation value, how the expectation value is calculated, or if you have ever seen this formula also, you might get to know that these operators are used, or the wave functions are used twice on the numerator, twice in the denominator. And because with the wave function you get an, so it should be multiplied 2 times in the numerator and 2 times in the denominator. When it will be multiplied 2 times in the numerator, it will become a square, and when it will be multiplied 2 times in the denominator, again it will become a square. So that's why this linear function will not be the answer, but the one which has a square should be the answer. Okay, now this whatever I am telling, and that's how you will reach out to option B as correct, but whatever I have told you is based upon logic and tricks, and this will only get to know, this you will only get to know when you will solve more question and get used to solving such questions, and you have the basic idea of it. You don't have to actually derive all these things in exam. I have derived it and I have explained you just to let you guys know that how to solve such question and what is the idea behind it. Okay, so that's it for this video. I hope you guys got to know a lot of things over here. Let me just tell you that we have our detailed gamma batch running on our app as well as on our website. The link is there in the description of this video. You can enroll yourself into that. Validity of that course is still 28th of February, so you can enroll and you can complete your physical chemistry syllabus. At least all the videos are there in detail, so you can watch those videos and your physical chemistry part will be covered from that particular batch. Also, we have launched our test series for GATE exam. You can buy that test series and start giving your mock test for the upcoming GATE exam. For CSIR NET exam, our test series is coming up in the next week, so you will be having that very soon on the app and on the website. So keep checking our app and website for that. All the previous year's question, all these previous year's questions has been covered in our ebook. So you can purchase our ebook where you can buy and you can just see all the questions solved over there. So this question was also solved in the ebook. So yeah, all the questions starting from CSIR June 2011 till CSIR June 2024 all are solved in our ebook. We have also a ebook for GATE exam, and that contains questions from GATE 2000 to GATE 2024. So all the questions are solved in detail on our ebook there as well. So you can buy our ebooks. You can also enroll yourself in our gamma batch, and you can also start giving your test series on our app. So that's all from my side for this particular video. I hope you guys like this series and we'll be having more questions. Do let me know if you have any suggestion for me for this particular video, and that's it. Take care. Bye bye. All the best.